Azuma, Akihiro Mizutani, and Dr. Bill Munro, and Kiyoshi Tanaka. Let's start. Okay, as well known, the quantum information processing composed of two big applications. One is quantum computation, the other is quantum communication. The big question in your field is how to realize such a field in quantum information processing now. Actually, if we see the realization of the quantum computation, we can easily find out the existence of many candidates. For example, somebody says that ion trap seems to be a good candidate to realize quantum computation. Somebody says that the superconducting qubit seems to be better. I cannot say which system is better than the other system. Actually, I can say one thing. Actually, the quantum computation is actually not fastidious about the types of physical system. And actually, any system is useful as long as such a system has a good controllability as a quantum system. This comes from the fact that actually the quantum computation is ultimately merely just a local information processing. On the other hand, quantum communication is essentially non-local information processing. That's why we need to have a good resource. Actually, quantum communication is fastidious about the types of the physical system. For example, photons are special. Namely, only photons are almost the only candidate to realize such a quantum communication. In fact, we have already achieved such a quantum communication by using direct transmission photons over optical fiber. In addition, we have already achieved, for example, 300-kilometer quantum communication. Actually, if we use ultra-low-loss fiber, in such a case, 400 kilometers is possible. But at this point, we have already known that this is actually distance limitation, which comes from the fact that the photon loss increases exponentially with distance. And so in order to overcome such a distance limitation, actually we need quantum repeaters. I think that so far, almost everybody have believed that quantum repeater needs not only photons, but also quantum memory. And but if we see this type of figure, actually this looks really strange because for all the other applications, and all the other applications can be done by using only a single system, essentially. However, the quantum repeater theory has enforced to use different physical systems at the same time in a hybrid manner. Okay, and so today I would like to focus on the quantum repeaters. And okay, as I said, yeah, only quantum repeater theories have enforced us to use different physical systems in a hybrid manner. One is photons, the other is quantum memory. If we see the realization of quantum memory, we can easily find out two types of different systems. One is an ensemble system, the other is a matter-qubit system in a cavity. Actually, but unfortunately, actually the German modern Razavi has shown that if we try to use ensemble system as quantum memory to realize quantum repeaters, actually we need infinite coherence time. More precisely, in order to perform the polynomial scaling quantum repeater for long distance, actually the very long distance coherence time is required. And in addition, from the theoretical viewpoint, we do not have a good way to make such an ensemble system fault tolerant because all of the old theory is based on the assumption on the use of the qubit system rather than the ensemble system. And so instead such an ensemble system, somebody suggests us that we need to use matter qubit surrounded by the good cavity. However, in such a theory always assumes that we need to use deterministic two-qubit operation for matter qubit, but each of which is surrounded by a good cavity. I don't know how to design such a system. In particular, actually the matter qubit system here is actually should satisfy not only Diviset's 5 criteria for quantum computation, but also is really difficult extra criteria on the efficient coupling with photons. Therefore, as long as it follows the dogma of the necessity of matter quantum memory, perhaps quantum repeaters may be much more demanding than a quantum computer. Okay, and so actually the quantum repeaters may be much more difficult than matter qubit-based quantum computer if we follow the dogma of the necessity of matter quantum memory. However, there is now a new quantum repeater scheme which is proven to be much simpler than our same type of quantum computer, and which seems to be an ultimate challenge for all optical approach existing in the conventional communication field. Actually, we call it all-photonic quantum repeaters. Thanks to this theory, actually, that we can exclude the necessity of the matter quantum memory in the quantum repeaters. Now, we can achieve the even quantum repeater by using optical devices alone. Okay? And in particular, our protocol uses just optical devices like this one. Linear optical elements like a beam splitter and photon sources, single photon sources, and photon detector and fast active field power techniques. That's it. We do not need to use matter quantum memory at all. Actually, thanks to such a feature, namely excluding the necessity of the matter quantum memory to perform the quantum repeater, our protocol has a distinguished advantage. First advantage is like this. Repetition rate of our protocol could be increased as high as 1 wants. Namely, our protocol looks like this. Namely, each repeater knows first to prepare the cluster state in the photonic system, photonic qubit, and such a cluster state photonic qubit is just sent it to the adjacent repeater node. In this case, that we can use, if we can use a single photon source like a machine, we can repeat until success. And that's why that the repetition rate of a protocol should be proportional to the repetition rate of the slowest optical devices. Namely, this is independent of the distance. In addition, our protocol works by using only telecom wavelength photons. Therefore, we do not need to use coherent frequency converter for photons with different wavelengths. In addition, that all optical components described here should be much simpler than matter quantum memory. This comes from the following fact. Namely, if we had a good matter quantum memory, in such a case, that matter quantum memory should be used to realize the demanding optical devices described here. However, the converse is not true. Therefore, the all optical elements required here should be much simpler than matter quantum memory. In addition, we just use the optical devices. Of course, at this point, we need to use a single photon as superconducting detector. But in principle, this type of protocol could work at room temperature. And more importantly, from a theoretical side, actually our protocol is the only scheme that has been proven to be much simpler than the KLM quantum computer, rigorously. Okay? And the main idea of our photonic quantum repeater comes from the time reversal idea. Such a time reversal idea is based on comes from for example, measurement device independent QKD or cluster state quantum computation. Okay, actually, our protocol is very simple. Namely, we just take the time reversal of the Duan-Liu-Pin-Schlag type quantum repeaters. But today, I am not going to the detail this protocol because I have already presented this content in the TYQI2016 in the last year. Therefore, if you are interested, please access to the YouTube. Right? And so today, I would like to skip the detail of the all-photonic quantum repeater. Anyway, I would like to summarize, find what is the merit of the all-photonic quantum repeaters. Okay, thanks to the finding of the all-photonic quantum repeater, we now understand that all the quantum communication is possible. All the quantum communication processing is possible by using optical devices. Of course, if we see the realization of quantum computation, photon should be a good candidate to realize it. This fact says that now any kind of quantum information processing is possible by using optical devices alone. In this sense, single photon seems to be in some sense unified language. We can compare everything, any kind of quantum information processing or complexity. We can just use such a single photon as a unit to compare the complexity of any kind of quantum information processing. Therefore, the photon seems to be a unified language in this sense. Okay? But today I would like to go next topic. And so now we now understand that everything is possible by using the optical devices alone. What is the next topic we should find out? Okay. The main question today is that is there a possibility we can find out intermediate protocol that can bridge the gap between the conventional quantum communication scheme and the future all-photonic quantum repeater? This is the question for today. In order to answer such a question, I would like to summarize the situation more precisely. And actually, if we see the conventional QKD scheme or quantum communication scheme, we can notice that this scheme has a limitation on the achievable distance. But the 300 kilometers is powerful enough to achieve, for example, intra-city quantum communication. Therefore, even in far future, such a conventional QKD scheme or quantum communication scheme should be used just to connect close parties. On the other hand, the all-photonic quantum repeater has, or just a usual quantum repeater, have no limitation on the achievable distance. Therefore, the quantum repeater should be used to realize intercontinental quantum communication scheme. In such a case, what is required for such a possible intermediate protocol? That should be this type of protocol should work in a more cost-effective way or efficiently than these two different types of quantum communication protocols. Namely, this protocol should work as to connect intercity communication. Okay, in the next, I would like to compare in terms of the practicality. Now, we have already know that actually the conventional QKD or quantum communication is now ready for practical use. On the other hand, even if we see the all-photonic quantum repeater is actually still demanding because we need to, at some point, quantum error predicting code or matter quantum memory or something. Of course, the all-photonic quantum repeater excludes the necessity of matter quantum memory. However, this protocol still needs to use a loss-tolerant code. What is required for such a possible intermediate protocol? Such an intermediate protocol should be intermediate in terms of even in terms of the practicality. Namely, such a protocol should not use such quantum error predicting code or matter quantum memory. Of course, this type of protocol has been proposed by Schonfen and Mosen, but unfortunately they use matter quantum memory, and so I just skipped the detail of the protocol. But anyway, I would like to find out this type of protocol. Namely, this protocol works without using quantum error predicting code and matter quantum memory. Okay, today I would like to present such a scheme to perform QKD, which can be called all-photonic intercity QKD in this sense. Okay, before introducing our new protocol, and I would like to quickly review the QKD schemes. Okay, I would like to start from the no-node QKD, namely just a prepare and measure scheme. Of course, this protocol includes TB84 or B92 or etc. TPS, of course, included in this class. Okay, in this case, as Barry has mentioned in the talk and in his talk, and actually now we understand that TGW bound, Takeoka-Guha-Wild bound. This bound says for given Roche channel, how much key rate is achievable in principle, namely where the Alice and Bob can allowed to use quantum computer. However, the bound says that there is upper bound for such a protocol. Namely, the upper bound is described like this. Here, the eta L represents the transmittance between Alice and Bob, and this L represents the distance between Alice and Bob. Anyway, the upper bound says that the upper bound is just proportional transmittance between Alice and Bob. This says that actually there is no hope to come up with a new idea to improve the performance dramatically. And so let's skip the improvement for this protocol here. Next, let us consider the single node QKD. The representative one seems to be like this, entanglement-based QKD. In this protocol, Alice and Bob, between Alice and Bob, there is a Charlie, right? And Charlie first prepared the entangled state, photonic entangled state. One of the particles sent it to the Alice side, the other particle is sent it to the Bob side by using optical fiber. Okay, vertical axis represents a time here. Okay, and in addition to that, we can now have another protocol called measurement device independent QKD, MDI QKD. In this case, that the bell pair source is just replaced by bell measurement module, right? And instead of measuring something, Alice and Bob just send the photons. This is just a simple time reverse relation. Okay, as you can easily find out that from this figure, these protocols are related by a simple time reverse relation. That's why the performance is almost the same. Namely, anyway, that both protocols scales as eta L. Namely, this because, for example, if we see the entanglement-based QKD protocol, if the one of the particle disappear under the transmission of the optical fiber, in such a case, this protocol fails. This fact represents by the square here. Okay, both photons should travel over the optical fiber. Okay, let us consider the possibility of the improvement for this problem. Actually, that there is no hope to improve further about the entanglement-based QKD because actually the pairing for entangled pair is determined in advance. Namely, before sending photonic state, we need to decide which particle should be entangled. That's why we have no hope to improve this protocol further. However, the situation changed for the MDI QKD. In this case, pairing has been made in the bell measurement module. In addition, the bell measurement is performed after the transmission of photons over optical fiber. Therefore, we can have option to perform the bell measurement here. In fact, we can find out such a way. Namely, this protocol has room for improvement by just replacing the vertical axis time with space. Namely, we just use the multiplexing rather than using the time order. Okay, now I would like to introduce our new protocol. We can call it adaptive MDI QKD. The concept is very simple. We just replace the simple bell measurement in the MDI QKD with an adaptive one. Namely, protocol looks like this. Namely, Alice and Bob first prepare a single photon state at the same time, and Alice and Bob just send such a many photon into Charlie's side. Charlie first performed the QND measurement to know whether the single photon successfully arrived or not. If the single photon has arrived, in such a case, by using the optical switch, such a surviving single photon is sent to the bell measurement module. That's it. And the same things happen for both sides. In this protocol, actually, thanks to the existence of the QND measurement and optical switch, this is just essentially we perform the bell measurement in an adaptive way, depending on the existence of photon loss. Okay. And please note that the transmittance between Alice and Charlie represented by eta L over 2 here. In addition, somebody says that the QND measurement seems to be difficult. However, not so difficult, I think. And actually, we can use, for example, linear optics-based quantum teleportation technique here. Namely, in order to perform the QND measurement, we first prepare the bell pair locally. After that, we just perform the linear optics-based bell measurement here. In such a case, the quantum state of the blue particle should be sent to the green particle. Therefore, we can use this type of protocol as an implementation of QND measurement here. Okay, and so, okay, let us go to the scaling problem. Okay, suppose that suppose that the number of the multiplexing is larger than the inverse of the transmittance between Alice and Charlie here, for simplicity. In this case, of course, the number of the multiplexing is larger than the inverse of the transmittance between Alice and Charlie. Therefore, at least one of the single photons should survive over the transmission of the optical fiber. Same things happen for both sides. Therefore, that Charlie should receive the one photon from Alice's side, one photon from both sides. After that, just such a surviving photon is sent into the optical Bell measurement module. Therefore, if Bell measurement module, and in addition to Charlie succeed to perform the Bell measurement, in such a case, Alice and Bob should obtain a candidate of the secret bit between Alice and Bob. This fact suggests that the key rate per pulse means that the number of multiplexing scaled as the transmittance between Alice and Charlie rather than Alice and Bob. Therefore, we should have a square root improvement over the conventional QK scheme. Okay, and we just borrowed the Short rescue type formula, and we just assume the very optimistic devices. I just correct the state of our technology. If we write the performance looks like this. Namely, here is a horizontal axis represents the distance between Alice and Bob, and the vertical axis represents obtained secret bit per pulse. Okay, this blue and green curve represent the TG double band and MDA-QKD performance of the MDA-QKD respectively. Our protocol is like this. So above here curve represents the performance of our protocol. As you can easily find out that actually for the 800 kilometer case, our protocols is 7 order of magnitude better than the conventional MDA-QKD. In addition, that because this type of improvement comes from the fact that the square root improvement, namely slope, is improved compared with the conventional QKD scheme. Okay, and so let us compare our protocol, for example, the quantum repeater with atomic ensemble. I just borrowed the figure from the review of the physics, and we just take the best performance described here. In such a case, for the 800 kilometer quantum communication, the key rate looks like this, 30 millihertz, or like this. On the other hand, if we use our protocol with devices with a 1 megahertz clock, in such a case, our protocol should present 90 millihertz final key rate. Therefore, that our protocol is better than the even quantum repeater with atomic ensemble. Moreover, our MDA-QKD protocol is now shown to have no scaling gap with an ultimate upper bound. And recently, we come up with the idea to generalize the Takeoka-Buha TGW band to be applicable to any network topology, any quantum network topology. Namely, we try to answer to this type of question, namely, what is the fundamental limitation for quantum network? Let us consider this type of very complicated quantum network. Here, each quantum node is connected by some noisy quantum channel. And here, Alice and Bob wanna share secret bits or E bits by using quantum channel in the quantum network and LOCC, local operation and classical communication. In such a case, that the final obtainable secret key or E bits is upper bounded by the minimum cut of the scarcity entanglement of the channel. By using this type of formula, of course, this is one of the, this formula is applicable to any types of quantum network. Therefore, we just apply this bound to our situation. Namely, by using this bound, we can show that the near optimality of our adaptive MDA-QKD protocol, and in addition, we can show that the near optimality of the existing quantum repeaters. Okay, I will try to summarize my talk, and I present the intermediate protocol called all-photonic intercity QKD. This protocol seems to bridge the gap between the conventional quantum communication scheme and the future all-photonic quantum repeaters. Of course, I hope that such a protocol is useful to realize all-photonic quantum internet in the far future. But anyway, I hope that this type of idea is useful for expanding the market of quantum communication and realizing the ultimate secure network. Thank you for your attention.
Questions? Yes. Koji, congratulations for the next talk. There is a reason why you do not, you know that the TYQI has been improved. There is a reason why you do not cite or you know that TGW has been improved, the bound.
Ah, yes, I know, sorry.
Yeah,
I forgot to refer to from bound, transient bound.
Yeah.
Actually, yes. Actually, now, for optical channel network or dephasing or anyway, the stretchable quantum channel, we have now tighter bound for such a quantum communication network. And namely, they can successfully derive the two-way quantum capacity for such a stretchable quantum channel. I need to mention that. Sorry, I forgot.
So, Koji, for your simulation page, you go to the simulation page.
Okay.
Almost the second last page.
Yeah, I'm very optimistic and this one.
What kind of model you are using for the QNB measurement for this one?
In this case, I assume the use of the ideal Bell pair source.
Ideal Bell pairs. Bell pairs. And
yes.
how about the Bell measurement? What's the probability for the Bell measurement? It's 100%. Because linear optics, you can only get about 50%.
Yes, I actually except for such assumption, I just model just a linear optical elements implementation for such.
So 50% from that.
Yes, yes. Okay. And we should write a similar graph if we change the parameters.
Yeah, I mean, I should say, I mean, this is a good idea, but the problem is to get an on-demand ideal in terms of the pairs. It's as difficult as get a good quantum memory.
Yes.
I mean, of course, if someday people get a good for the pairs from fundamental quantum dot and get a very high vacuum efficiency, this protocol may work. Yeah.
Yes.
Otherwise, this is also another challenge.
Yeah, in my opinion, that of course, one way to realize a single photon source is we need to matter quantum memory power. But the other way to realize single photon source, we just use optical switch.
Yeah,
right.
I agree. But to get the very good on-demand in terms of the pairs, you need matter quick element.
Okay.
I mean, generally people say parametric conversion doesn't work, right? You know that.
Yeah, parameter. But I don't know, but I have no.
But yeah, it doesn't work. I tell you, it doesn't work. And for the quantum dot source, it's very hard to get high efficiency and high fidelity one.
Okay.
But still, yeah, it's good field. Yeah, it's good field. But yeah, take time from me.
Okay.
Was there a question in the back? Question. Okay, maybe I asked a quick question that the comparison that you had with the quantum repeater, the review paper.
Yes.
Isn't it the case that for the repeater case, we have only one memory per node?
One memory per node. In this case, in the level of the physics, they just use one memory per node.
So in terms of and in your system, you're using multiple spatial modes, so yes. The comparison is a bit unfair in that sense, isn't it?
I don't think so, because I just divided this final key rate per optical channel. In the case of the DLCZ,
no, but we can discuss it later.
Okay,
because I think once you have an array of memories, it takes less time. So, but let's thank this Koji again. Very nice talk.